Hello everyone. In today's lecture we will talk about NMR spectroscopy, and in this lecture I'll try to give you basic introduction how NMR spectroscopy works. NMR spectroscopy means nuclear magnetic resonance spectroscopy. This is a very powerful technique. It's a non-destructive in nature. Non-destructive means the sample loss is not there. You can reuse sample after performing NMR. And in fact, in case of organic chemistry labs where chemical compounds are being synthesized, NMR is the first choice to find out whether synthesized compound is the correct one or not. And not only small molecules, but even the structure of larger molecules like proteins or DNA, that also can be solved using NMR spectroscopy. And the molecular dynamic studies, diffusion coefficient, rate constants, activation energy, thermodynamic properties of molecular reactions, those are also determined by NMR spectroscopy. And one of the very powerful diagnostic tool that's called MRI, magnetic resonance imaging, that's NMR tomography, that's also based on the principle of NMR spectroscopy only. So a nuclei, we know that nucleus of atom contains protons, and protons are charged. So, and we also know that when a charged particle is having a spin, that creates a magnetic field. So all the nuclei of atoms which contain a spin, that behaves like a magnet, because that has a resultant magnetic moment. And this magnetic moment depends on the angular momentum of that nuclei. So from here we can understand that a nuclei of atom which is having nucleus of atom which is having a spin, that behaves like a magnet, because that creates a magnetic field as it's having charge and it's moving, it's spinning. So that nucleus which is spinning, that behaves like a magnet. And not all the atoms have the magnetically active nucleus. For example, the H1, the hydrogen atom, H1 contain one proton. So all the atoms, all the nuclei which have odd number of protons or odd number of neutrons or both, they are having a resultant spin, and those behave like a magnet. And those nuclei, they are detected in NMR spectroscopy. So H1 is naturally abundant, is magnetically active. The natural abundance is 99.985%. C13 is also magnetically active. C12 is naturally occurring, but C12 is not magnetically active. C13 is, but C13, the natural abundance is very low, it's just more than 1%. Similarly, N15 nucleus also is having resultant magnetic moment, and that also behaves like a magnet, but N15 is also is not naturally present. F19 and P31, those are other nuclei which are magnetically active, and those are abundant in nature. So if you want to determine the structure of a molecule, you in NMR spectroscopy, you try to detect the type of nuclei in that molecule and their neighborhood. For example, if you are detecting proton H1 in a compound, in order to know its structure in NMR spectroscopy, you call that H1 NMR or proton NMR. Similarly, if you are detecting C13 in a compound, is called C13 NMR. But C13 and 15, they are not naturally present. So in order to use them, to detect them, these atoms are introduced from outside. For example, if you are working on a protein or you are synthesizing a compound, and in order to detect C13 in the compound, you need to add C13 atoms while synthesis reactions. Or when you are producing proteins, you need to provide the compound having C13 in the media. So the proteins are synthesized having C13 atoms. So you can detect eventually that in NMR. So H1 NMR is very commonly used. So when you have a spinning nucleus, that creates a magnetic field. It has a magnetic moment, and we know that magnetic moment is a vector quantity, so that is represented with the help of an arrow like this. And when you have a compound having multiple nuclei in that compound, multiple atoms, and you don't have any external magnetic field applied, in that case the magnetic moment of all these nuclei, all these atoms, is randomly oriented. They are going in different direction. So the nuclear magnets are randomly oriented in absence of any external magnetic field. But if you keep that compound under a fixed strength magnetic field, in that case these the nuclei, they arrange themselves in the direction of the applied magnetic field. For example, this is the direction of applied magnetic field from outside, and these are the nuclei under influence of this field. So these nuclei may arrange themselves in the direction of the magnetic field, or in lesser cases, some of the nuclei may arrange their magnetic moment in opposition to the applied magnetic field. So the nuclear magnets, when you apply outside magnetic field, you keep the compound under external magnetic field, the nuclear magnets are oriented with or against the B naught. B naught is the applied magnetic field. So there are two orientation possible when you are applying magnetic field from outside on a compound which is having magnetically active nuclei. And these two states, if this is the direction of the applied magnetic field, so if a nucleus is orienting in the same direction of the applied magnetic field, that's called alpha spin state. It's a lower energy state. Or some of the nuclei may arrange their magnetic moment in opposition to the applied magnetic field. So that's called beta spin state. Beta spin state is higher energy state, and the energy difference between alpha and beta depends on the magnetic field applied. The energy difference would be delta E is equal to gamma h upon 2 pi into B naught. So gamma is a gyromagnetic ratio. That's a fixed number for a nuclei. H is Planck constant, and 2 pi, so this is everything is constant here except the B naught. So energy difference would depend on the magnetic field applied from outside between alpha and beta spin states. So when you keep a nucleus under external magnetic field, it start the magnetic moment, magnetic moment vector of that nucleus. See this direction, this is the magnetic moment of the nucleus vector, and this is direction of applied magnetic field. So this vector start precessing in the direction of the applied magnetic field. So this precession frequency is also called Larmor frequency. So the Larmor frequency refers to the rate of precision of the magnetic moment of the proton. Proton is the one, the nuclei we are detecting, around the external magnetic field. So if this proton is precessing in the direction of applied magnetic field, this represent alpha spin state, and this also called spin plus half. Or if this vector is precessing against the applied magnetic field, this is called beta spin state, and the spin is represented by minus half here. So there are two transitions possible in case of a nucleus when it is kept under external magnetic field, and the energy difference of course would depend on the external magnetic field applied on this nucleus. The Larmor frequency is represented by omega, and that is equal to gamma B naught. B naught is the external magnetic field, and gamma is a gyromagnetic ratio. That's a fixed number for a given nuclei that would depend on charge and mass of that nucleus. And it's basically give you an idea about the precession frequency, how much is the precession frequency of a nucleus under given magnetic field. That's represented by gyromagnetic ratio, which is a fixed number for each nuclei. So when you increase the applied magnetic field, you can increase only difference in the energy of alpha and beta spin state. Alpha and beta, they cannot be interconverted just by changing the magnetic field. So for example, here if you apply magnetic field of say around 7 Tesla, the energy difference between alpha and beta spin state of the proton is 300 megahertz. Or if you increase to around 14.1 Tesla external magnetic field, the difference becomes 600 megahertz, the difference of alpha and beta spin state energies. So in fact, NMR spectrometer is defined by this energy, this 600 megahertz or 300 megahertz. So that basically represent, for example, if you have a 600 megahertz NMR machine, that simply means you have a magnet which produce around 14.1 Tesla magnetic field, and that is basically giving frequency difference of alpha and beta spin state of 600 megahertz. So the frequency, the Larmor frequency defines the type of or strength of a NMR spectrometer. So alpha spin state and beta spin state also can be interconverted. Alpha spin state is a lower energy state. Most of the nuclei, when they are kept under magnetic influence, they align themselves in the direction of the applied magnetic field. That's what we are calling alpha spin state. But this alpha spin state can be converted into high energy state, that's a beta spin state, if electromagnetic radiation is applied from outside, which can be absorbed by that nucleus, and the range of the electromagnetic radiation which is absorbed by the nucleus is radio frequency waves. That's lies from 100 kilohertz to 300 gigahertz. So between this range, electromagnetic radiations are absorbed by the nucleus. So if a radio frequency pulse is given to alpha spin state nucleus, it absorbs that radio frequency pulse, the energy, and convert into beta spin state. And when the pulse is removed, the beta spin state is relaxed back to the alpha spin state, and simultaneously releasing the same amount of energy of the same frequency what was absorbed. So this released energy, released frequency, this wave is basically the what is detected as a signal in NMR spectroscopy. And for example, if you are keeping a compound under some magnetic field, all the nuclei, most of the nuclei, in fact, they will attain the alpha spin state. But when radio frequency pulse is given, all the nuclei, they go back to the beta spin state, high energy state, and that where all the nuclei are in beta spin state, this is called magnetic resonance. So all the nuclei in the compound, they are in resonance by absorbing radio frequency pulse. So we can understand it in a better way. For example, this is a nucleus. This arrow represents the direction of the magnetic moment of the nucleus, and if you keep that nucleus into some magnetic field which is going into this direction, so that's a B, applied magnetic field from outside. So because this nucleus is also a magnet, and you are putting this magnet under outside magnetic field, so as a result, this magnet will align itself into the direction of the applied magnetic field in this way, or in opposition to the applied magnetic field this way. So this is called alpha spin state, which is a lower energy state. Most of the nuclei, they arrange themselves in the direction of the applied magnetic field in lower energy alpha state, and very few nuclei may also orient their magnetic moment vector in opposition to the applied magnetic field. That's called beta spin state, is high energy state. And now we understand this better having this example of you have one nucleus which is in alpha spin state, and there is no electronic cloud in the vicinity. When you say no electronic cloud, or electronic cloud simply means, for example, if you are detecting this proton here, so in this proton, if you are detecting this is proton, so the electrons from oxygen also are there in the neighborhood of this proton, and they also influence the magnetic property of this nuclei. So this is called dimagnetic shielding. So you have one proton where there is no dimagnetic shielding, there is no electron in the vicinity. For example, another proton which is having electrons in the vicinity. Another atom is covalently attached, and electrons of those atoms are also in the neighborhood. So, and you are keeping them under a fixed magnetic field. So the presence of electrons here, because electrons are also moving and they are also charged particle, so they also create a magnetic field. So if there are electrons in the vicinity of this proton, they also create a magnetic field which resists the applied outside magnetic field. It simply means the presence of these electrons reduces effective magnetic field on this nucleus. So that is called diamagnetic shielding. So now this alpha spin state, you give a pulse of radio frequency radiation. So this nucleus will absorb and it will go back to the beta spin state here, and say it has absorbed the energy amount E1. So E1 energy is absorbed by this nucleus, which is not having any diamagnetic shielding. Now you repeat the same thing with the proton, which is having diamagnetic shielding. Because it's having electrons in the neighborhood, it is shielded, so it will absorb radio frequency radiation, it will turn into beta spin state, and it will absorb energy, say E2. So in this case we can easily understand that the E2 is always smaller than E1. Why? Because the magnetic field reaching to this nucleus, which is shielded, is less. That's why it takes lesser energy in order to convert into beta spin state, and that's also called as magnetic resonance. So if you plot this information in form of a graph, on x-axis you have energy, y-axis you have this peak abundance, and this is 0 here. This is, so if you start from here, there are two protons, one is shielded, another one is deshielded. So you have shielded proton means where electronic clouds are there in the vicinity, which absorb energy E2. In case of deshielded proton, it absorbs energy E1, and of course E1 is higher than E2. So you get a spectra like this, you get a signal like this. So these two protons will give you different signal. Those two are protons only, but they have different environment. One is having electrons in the vicinity, other one is not having electrons. So one we call deshielded, other one a shielded proton, shielded nuclei. So in that case you get two peaks, you represent them A and B. So A nucleus is giving peak at high frequency, B at lower frequency. So that's what you do in NMR spectra basically. So you plot energy, the energy absorbed by the nuclei in order to gain the magnetic resonance in NMR spectrometer. And the difference of the peak is because of effective magnetic field. The effective magnetic field, this is the magnetic field applied B from outside, and the effective magnetic field on this nucleus would be equal to the B applied from outside minus B local. B local means if there are electrons in the neighborhood which are also creating some magnetic field, that's the B local here. So in case of deshielded proton, deshielded nucleus, where there is no electron in the neighborhood which are affecting properties of this nucleus, in that case B local is 0. So B effective would be equal to B applied in the deshielded proton, in case of the deshielded proton. So it will be high. So B effective will be B applied. So B effective would be high in this case. So high B effective means the proton will absorb high energy in order to attain resonance. In contrast, if you have electronic cloud in the vicinity of the proton, those electrons also create a magnetic field which resists the magnetic field applied from outside. So the magnetic field reaching to the nucleus, this proton, is less. So B effective here would be B applied minus B local, but B local is having some value here due to presence of the electronic cloud in the vicinity, in the neighborhood. That's why the B effective in this case would be less than B applied. So less B effective means it will absorb, this proton will absorb less frequency, less energy in order to convert into beta spin state, or what we call in order to attain the magnetic resonance. So if we summarize this, if you have a shielded proton, if shielding is high, the B effective would be less. B effective less means it will absorb less energy, and the peak is called upfield. So for example, here if we start from this direction, you have energy increasing in this direction. Here you have a reference peak that's at 0. So the peak coming close to 0 is called upfield peak, for example here. So the protons which sense a smaller effective magnetic field, so they come into resonance at lower frequency, and this peak is called upfield peak. Similarly, if you have a deshielded nuclei means the B effective will be more. B effective more means it will absorb high energy in order to resonate, and the peak is called downfield. So downfield means away from the zero, you have higher energy. Higher energy peak is downfield, low energy peak is called upfield in NMR spectra. So in NMR, the radio frequency pulse can change alignment of alpha spin state into beta spin state, and the frequency required, the radio frequency energy required by each nuclei in a molecule is different because of having different environment. So that's why you can get multiple different peaks of for example proton in NMR spectroscopy. And one after the pulse is given to the nuclei, absorb the pulse, they become in high energy state, that's called beta spin state or magnetic resonance state. And then after the pulse is removed, the radio frequency pulse is removed, the nuclei relaxed back into the natural alpha spin state. So this is called relaxation process, and during relaxation the energy released, the radio frequency energy released is detected, and that is shown in terms of NMR spectra. But we know that because there are, for example, there are multiple nuclei in a compound, and all the nuclei have given simultaneously given radio frequency pulse. So all the nuclei will emit different radio frequency radiation, but we are detecting them simultaneously. It simply means that different waves will combine together, or they will interfere with each other, and as a result of constructive and destructive interference, you get a spectra that is time based here. So something like this. So this is time based spectra where the frequency, the radiation from all the nuclei is merged together, but we need to separate all the frequencies from this spectra, from time based spectra, and that is done by a mathematical transformation called Fourier transformation, a mathematical operator. So Fourier transformation can be applied to these waves, and that's how it is converted into frequency based spectra here. So this is also known as chemical shift, the frequency or energy, or represented in parts per million, that we'll discuss in the next lecture. So this is the final spectra you get from a NMR spectroscopy, where you have energy on x-axis and abundance on y-axis. So now let's look at an example of some compounds, how they behave, what kind of peaks they will give in NMR spectroscopy. For example, you have a compound CS3CH2Cl, ethyl chloride. So if you keep this compound into NMR spectroscopy and you try to detect H1 hydrogen atoms, how many peaks would you get? So we know that in NMR spectroscopy, all the protons which are having different environment, they give different peak. So first we need to find out on the basis of environment how many types of hydrogen protons are there. So you see here in CS3 means you have 3 protons, and these three protons are at equivalent positions, and they can be interchanged also. Same time, the second group is methylene group here. So all these 3 protons which can be interchanged, they are at equivalent position, they have identical environment. It means these three proton of methyl group, they are one type. They all three will give single peak in NMR spectroscopy. Similarly, this CH2 group here, to see these methylene group 2 hydrogen atom, they are also at the equivalent position. They have same environment. One side they have methyl group, other side they have Cl atom. So these two protons are also have the same environment. So the CH2 proton will give another peak. So that's why if you, and one more thing here, the CS3 proton, they are having they are most shielded here. Most shielded means the protons of carbon also would be here. Sorry, the electrons from the carbon would be in the vicinity of this proton. So that will make it more shielded, and we know that shielded proton means it will absorb less energy in order to come into resonance. Whereas in case of these methylene group protons, they are deshielded. Why they are deshielded? Because they have a Cl atom in the neighborhood, and we know that Cl is more electronegative, so Cl will pull the electrons of carbon towards itself, so the electron would be less in the vicinity of these methylene protons. So it means these methylene protons are deshielded in comparison to the this methyl group protons, so it will absorb high energy in turn. So if you plot a spectra, you will see that the A type, we call them A type, the methylene group having these A type protons, they are deshielded, they will absorb high energy. So in a spectra you will see a peak more downfield. Whereas the CS3 protons, they are shielded, they have more electronic cloud in the neighborhood, so they will absorb lower energy and the peak will be more downfield here. So B peak would be here. So in ethylene chloride compound, you will get two peaks, and you see here the one peak, this signal is bigger than this signal. So that basically the strength of the signal, the area of the peak represent how many protons are contributing for that peak. So for example, for B here, there are 3 protons. They are coming from the methyl group. A types, they are coming from methylene group, they are 2 protons. That's why the peak is smaller in size. Now look at another example. You have a compound called C3H7Cl. It has CH vibration, many CH bonds, there is no double bond, and we need to know whether what compound this is. If you look at it could be either 1 chloropropane or 2 chloropropane. By NMR spectroscopy, we can precisely find out whether it's a 1 chloropropane or 2 chloropropane, which isomer is there. So for that, we just look at the how many peaks 1 chloropropane or 2 chloropropane would give in NMR spectroscopy, where you're detecting H1. So basically H1 NMR. So you see here you have this CH2 group. These 2 protons are equivalent position. So they will give one peak. We are calling them A-type peak. They have a neighborhood Cl atom. Other side you have CH2. This CH2 we are calling C-type. This is also having different environment. One side you have CH2 group, other side methyl group. So this is also unique. And this methyl group CH3 is also unique. All 3 protons are equivalent position here also. So they will give single peak, and that we are calling B-type peak. So 1 chloropropane would give 3 different peaks in NMR spectra. Whereas if you look at a 2 chloropropane, just look at what kind of what different type of these protons are there depending on their unique environment. The methyl group here, this methyl group is having in vicinity this CH group and Cl. Similarly, this methyl is also having same environment. So these 2 methyl group, we are calling them B types. So they these 6 hydrogen from 2 methyl group will give a single peak here, because these both methyl have this identical environment essentially. Whereas this CH group here, it is having different environment than methyl group. In vicinity you have both side, you have methyl groups and Cl atom here. So we are calling this A type peak. This A and B type is just for discrimination, to differentiate them. You can give them whatever number or name, doesn't matter. So basically you will get 2 peaks from 2 chloropropane, the A types here and B types here. Again, you look at the size, the B type would be much more bigger, the signal for B, because you have 6 protons involved in this peak, whereas you have a single proton forming the A peak. So by NMR spectroscopy you can differentiate different type of compounds also. In a typical NMR spectrometer, you have a sample tube where you keep a sample, and that's surrounded by a superconducting magnet. The magnet of different strengths are available magnetic field. For example, I think today's time you have up to 1500 15 megahertz frequency magnets are also available, which are used for determination of structure of molecules. Then you have radio frequency generator. You give radio frequency pulse to the sample, and then the emitted frequency is detected by the detector, amplified and recorded by a computer, which shows the NMR spectra. So key points from this lecture, I know we have understood that due to presence of charge and spin, a nucleus behaves like a magnet. And NMR operates by applying a magnetic field to the nuclei. We put a compound, that compound under a magnetic field, and then measure the amount of energy required to resonate those nuclei. To resonate nuclei means have alpha to beta spin state conversion. And nuclei in different environment, they require different amount of energy to bring them into resonance, because environment affect the magnetic property of the nuclei. That's what we have seen. And in NMR spectrum, it provides a signal representing the necessary energy change to bring each nuclei into resonance. For example, in case of, if we look at the ethanol NMR spectra, CH3, CH2OH, there are 3 types of proton here, one forming methyl group, then methylene group, and OH group. So you get 3 signal from the NMR spectra of ethanol. So these 3 signals give you an idea about that there are 3 different type of proton in the compound. And the peak strength also, you can see CH3 is longer one because there are 3 proton contributing to this. Then CH2, there are 2 proton small, and OH proton is just single proton here with a smaller one.